Very good morning, friends and my dear students. Warm welcome to all of you. Today we are going to see the typical stress strain curve video lecture and its important or salient points on the stress strain curve. So here I am taking the material of mild steel. You know that the mild steel is of the Poisson ratio 0.25 to 0.33. That is 1 by 2 to 1 by 4 to 1 by 3. So before that, we are going to see what is the statement of Hooke's law. The Hooke's law states that the stress induced in the material is directly proportional to the strain if you are applying the load within the elastic limit. The point within the elastic limit is very much important. Therefore, stress is directly proportional to the strain. So here, the stress is denoted by sigma and strain is denoted by epsilon. So therefore, sigma is directly proportional to the epsilon. Now we are equating it. Sigma is equal to some constant into the strain. So if you are taking stress by strain is equal to a constant, so that is nothing but the Young's modulus. So therefore, stress by Young's modulus is equal to strain. If we want the strain, so stress by Young's modulus, and if you want to find the Young's modulus of the material, capital E, the stress by strain is equal to the Young's modulus. This is about the Hooke's law. The Young's modulus of the steel material is normally 2 into 10 power 5 to 2.22 into 10 power 5 Newton per square millimeter or megapascal. Now I am going to show the typical stress strain curve for mild steel. So you can see, if you are plotting this stress in the y-axis and strain in the x-axis, you will get a lot of important point on the stress strain graph. The first point, which is called as point A, which is nothing but the limit of proportionality. The limit of proportionality is defined as the strain is a linear curve. Stress strain curve is a linear curve. So that means the stress by strain, wherever you take, the slope will be equal. So that is called the limit of proportionality or proportional limit. The next important point on the stress strain graph is Young's modulus or modulus of elasticity. The modulus of elasticity is very important factor in designing any of the material, either in the structural design or in the mechanical design or the production or the aeronautical design. So the Young's modulus is defined as the ratio of the stress to strain. So therefore, Young's modulus capital E is equal to sigma by epsilon. The unit of Young's modulus is Newton per square millimeter or MPa. Next point on the stress strain graph is yield point. There are two yield points for mild steel. For other material, you will not get a second yield stress or yield point. But here, if the manufacturing is a perfect one, you will get two yield point. The first one is called as upper yield point and the second one is called as lower yield point. So that means what? The material slowly started yielding. That means the deformation will be there even for a constant stress. The case of upper yield point and lower yield point. For a constant stress, the elongation will be taken place. If it is a tensile load, if it is a compressive load, compression will be taken place. So what is called as upper yield stress? Upper yield stress is defined as the upper yield load divided by area of cross section of the bar. Yield load I will call it as P suffix y, and the area of cross section is capital A. So therefore sigma y suffix u, that means for upper yield stress, is capital P y divided by capital A in Newton per square millimeter. Similarly, you can find the lower yield stress. The lower yield stress normally, which will be of lesser than the upper yield stress. You will not get the lower yield stress or the second yield stress in any other material except the mild steel. Then the next important point is the ultimate stress or the ultimate point. If you are loading the material beyond the yield point, what will happen? The stress is not directly proportional strain. The parabolic curve will start. That means once you are removing the load slowly from the material, it will not regain its original shape and position. So that means you are loading beyond the limit. So therefore, the ultimate point or the ultimate stress is going to happen. So that is the maximum capacity of the material to withstand the load without any failure. The ultimate stress sigma suffix u is equal to ultimate load divided by original area of cross section of the bar. So P suffix u divided by capital A. P suffix u is nothing but the ultimate load or ultimate capacity of the material. Then the last important point on the stress strain graph is the failure load. The failure load is denoted by F. The corresponding stress is sigma B, that is for breaking stress or failure stress, divided by original area of cross section. So therefore, sigma B is equal to capital P suffix B divided by area, where PB is nothing but the breaking load of the material of the body. The unit is Newton per square millimeter. So from this you can find the various important points on the stress strain graph. The Young's modulus, once you know the Young's modulus, you can able to find the shear modulus and the rigidity modulus. The shear modulus is defined as the ratio of shear stress by the shear strain in Newton per square millimeter, and the bulk modulus is defined as the direct stress of the material of the body divided by the area of the strain. So it is denoted by the notation capital K, that is equal to direct stress sigma suffix P divided by the epsilon. So this way you can able to get the corresponding various moduli of velocity of the material. Similarly, you can able to find the Poisson's ratio, which is denoted by mu or 1 by m, that is equal to the ratio of lateral strain by linear strain, epsilon lateral divided by epsilon. So there is no unit for the strain. Similarly, you can find the volumetric strain if you are applying a direct stress or volumetric stress. So volumetric strain epsilon v or small ev is defined as the ratio of change in volume to original volume of the body. So that is delta v by v. So this is about the typical stress strain curve. So on the curve we can able to find the various important or the salient point on the material of the body. You can able to find the various moduli of elasticity like Young's modulus, bulk modulus, and shear modulus. So with this, we can go for the next video, which is based on the problematic things in the case of the stress strain salient point. Thank you very much for patient listening. God bless. Walka Vajagam, Walka Valamuda.